Fairly often, I get asked questions about how I got started podcasting with the Breaking Math podcast, and I'll often be asked this question by those who are thinking of starting their own podcast. That is, people who are looking to tell a story or share their unique wisdom with a larger audience or their passions, or maybe just advertise their business or services. I usually like to start this conversation by either showing off or telling about our preferred podcasting platform, Zencastr. Zencastr is essentially an all-in-one podcast hosting platform. On this platform, you can do everything from recording your episodes to editing your audio and video files to distributing your podcast to all podcasting platforms, including Apple Podcasts, Spotify, iHeartRadio, and wherever else podcasts are played. Now, there's more. When I first began podcasting, I used to get very nervous about how I would sound. I would sometimes stutter or have awkward pauses or other audio blemishes in my recordings. Now, Zencastr has a new suite of AI tools in their post-production process that make you sound really smooth. They automatically take out any of the ums or ahs in your recording. Also, they automatically take out any of the awkward pauses in your discussions. The tools will also help you set the right loudness and balance all the levels while reducing any background noise, all with the click of a button. Doesn't sound too bad, does it? You really should check it out. Really, the world needs to hear what you have to say. In fact, I'm going to give you a code below to help give you a large discount. It's all one word: Breaking Math. Go to zencastr.com/pricing and use my code BREAKINGMath, and you'll get 30% off of your first month in any Zencastr paid plan. I want you to have the same easy experience I do for all my podcasting content needs. It's time to share your...
What's the easiest choice you can make? Window instead of middle seat? Picking a vendor who sends a great gift basket? Outsourcing business tasks you hate? What about selling with Shopify? Whether you're selling a little or a lot, Shopify helps you do your thing, however you cha-ching. Shopify is the global commerce platform that helps you sell at every stage of your business. From the launch your online shop stage to the first real-life store stage, all the way to the did we just hit a million orders stage. Shopify's there to help you grow. Whether you're selling scented soap or offering outdoor outfits, Shopify helps you sell. Wherever and whatever you're selling, Shopify's got you covered. Sign up for a $1 per month trial period at shopify.com/try. Go to shopify.com/try now to grow your business, no matter what stage you're in. Shopify.com/try.
I'm Sofía.
And I'm Gabriel.
And you're listening to a Breaking Math Problem episode all about conceptual calculus and specifically rates of change on how they relate to one another in a problem.
This is a very, very exciting episode. This episode, you will see, involves a fluid filling up a human skull. So just hang tight and you will see what this is all about.
Yes, but before we get down to the episode, and it's October, right? We're doing October stuff.
No, dude, it's freaking March, yo. But
it's October in the Southern Hemisphere, right?
It's like October. Yeah, right. You're right. I mean, when you think about it that way, it's like October. It's just not. You know what I mean? Does that make sense?
Yeah, because March is the third month.
Yeah.
October's the 10th month.
Which, if you subtract 1, think about this.
Yeah,
you
3
get
squared.
9.
Yeah,
which is 3 squared. So it's like October.
I know. I see where you're coming from.
Yeah.
But before that, we have some plugs. And before we deliver our plugs, our website is still down. I don't know what's happening with the domain.
We have to fight some pirates, but we believe that the website should be up again soon.
Yeah, and if not, what we're going to do is we're going to just register a new domain.
Yeah.
And we're going to put a little note at the beginning of every episode that we have telling everyone about the new domain. It'll be cumbersome, but, sometimes if you're like me and you may or may not have ADHD, dealing with internet pirates is a hassle.
Yes, it is. It is, yeah. When we were talking earlier just about how October is kind of like March in a way, when you think about it, I think if you get into numerology, maybe someday we should do a numerology episode. What do you think?
I was thinking early April.
Very early April. Let's do a numerology episode in very early April. I think that'd be a good time to do it. That'd be great. I think it'd be a very entertaining episode. Anyways, moving on.
We also have a Patreon, patreon.com/breakingmath, and I see that people are starting to help us out on that quite a bit. It's helping us out a lot. If you can,
it's hugely, guys. It's hugely appreciated. It really is. I mean, it's wonderful. We love doing journalism, and our dream is to do high quality journalism, not only for math but other subjects as well. And we'd love to do that, and it's made more possible with your Patreon donation. So thank you sincerely. It's very much appreciated. It is possible to be advertisement free if we have sufficient Patreon donations. That would allow us to do what we want to do.
Yeah, we want to make this an ad-free experience for you. I know when we came out with a couple of reruns, I think I accidentally put an extra ad, including the baked-in ones. Oh. So sorry for all you who had to experience that. But anyway.
Quite all right.
We have tier where we deliver outlines to you. We do the episode without any ads on the Patreon. If you want it there, that's only $5 a month to get that. And we also have a Facebook poster store at facebook.com/breakingmathpodcast. Just click on store. And we brought the price down to $15.15 for a tensor poster.
Huge news. We now have discounted our I should say Sophia's. I didn't do a whole lot. No, that is Sophia's project. Full disclosure, I didn't have a whole lot to do with that aside from encouraging Sophia to finish it and to print it. I did encourage you to finish it.
Yeah, it took months.
I had to write you about, hey, how's the poster coming? And you're like, it's almost done that. I don't feel like it.
Yeah, because I remember I designed one version of the poster, and it was kind of it wasn't as detailed as this one.
Yes.
But yeah, so the poster has if you're in a vector analysis class, the poster will have some fun stuff for you. Yes. If you're a physicist, you'll like it. If you like having cool things up in your office, you'll like it. I think it's 24 by 36 inches. So it's a big poster that you're getting, and we send them in poster tubes so nothing's wrinkled. And
Correct. And we have now changed the price. It used to be pi to the e dollars. It is now only e to the e dollars. So, if something to the 2 is squared, what is e to the... It's like between squared and cubed.
It's cubed.
Take e and do something to it that is not really squaring, but not really cubing. It's like a fractional dimension, which, you can hear more about on the Chaos Theory episode. But
well, actually, just real quick, if you take something to the 2.5 power, you're squaring it and then multiplying it by its square root. Oh, and if it's 2.75, then you're multiplying that by its fourth root. And the infinitieth root of any number is 1. Yeah. So it's get closer and closer to 1. But basically, that's how you generalize that. And also, you can find updates on the show on Facebook. And that again is facebook.com/breakingmathpodcast. And we're on Twitter at breakingmathpod. And we're trying to get a little bit more active on Twitter. But send us your questions and thoughts there. We'd love hearing from you.
Yes, absolutely. We certainly would. So without further ado, this is a fun episode. This is a problem episode, and it involves filling a human skull with liquid. So why do we want to talk about this? Do we want to talk about what inspired us to design this problem?
It's a very classic calculus problem, but I've always found it very poorly explained because the entire problem can be explained using thought analogy, and we could do it on the podcast, but usually people take derivatives on paper and apply it, and it's actually very confusing. You substitute variables and you do all this stuff for a calculus concept, and yes, you do need to know how to do that. If you're doing it on paper, you will eventually need to know how to do that. But if you had to learn how to write English before knowing how to speak it or something like that on paper, you can see how I'm not sure if that's a great analogy, but you know what I'm getting at.
Yeah, exactly. And really, we wanted to do it because, calculus is amazing. Rates of change are amazing. Writing the outline for this episode, we just kept laughing at all of the crazy thought experiments that you can do with calculus. So I think that we were trying to, we like to make problems relatable and exciting. And I thought, well, let's do, like a problem. It's exciting, like Fast and the Furious or something. But we thought, what's relatable to most listeners? So, of course, the human skull. Who would not want to have a human skull of their enemies? You know what I mean? I certainly would. So then, in designing this episode, I thought, now, wait a minute. is it even legal to have a human skull? So Sophia had to Google search, is it legal to have a human skull?
Yeah, I had to Google search.
Yes, I made you Google search it. And what did you find out, Sophia?
What I learned from is that in the United States, at least, most states do not have restrictions on owning human body parts. The exceptions are Louisiana, where it's illegal. There's Georgia and
But everywhere else it's legal to have a human skull?
Georgia and Tennessee. You can buy, own, sell, and trade human remains as long as you're not going across the state border.
Correct. So just be careful with that. We want to make sure we stay in the confines of the law.
And speaking of the law, you also cannot in the United States own any. You can't grave rob anymore. You never could, but now it's really frowned upon.
Yep.
God. You can't murder. Native people, their graves have been desecrated for a long time, so there are restrictions on that. Very good restrictions on that.
We support that.
Nature found human bones, so you can't just go out into the woods and be like mine. And viable tissue. So if you cut off your foot, make sure you pickle it before selling it, or else it's illegal.
That's right. You have to pickle your body parts before selling them. We don't want anybody to get in trouble here on the Breaking Math podcast. So really, no, I'm just kidding. Maybe this episode had to deal with filling up a container of an obscure shape, and maybe it just so happened that Sophia said, "What about a human skull?" And that was the whole reason for all of this. Like, what else?
Chose the human skull for a good reason. It's a very irregular shape.
Yes.
And we need a very irregular shape in what we're talking about.
Exactly.
And
now we're assuming the human skull, all of the holes in it, except for maybe a hole in the top. First of all, we've removed a portion in the top so liquid can be poured in, and we've filled in the other holes with something like spackle. By the way, if you have a human skull and you need to spackle it, can I take a moment to recommend any of the spackle that they have at any of the hardware stores, like House Depot or Bros or any of those places?
Bros. Yes, any spackle will do on a human skull. Human skulls are remarkably porous.
Yeah, just go to your local hardware store and say, hey, I need some spackle for a human skull. What do you recommend? The guys from Breaking Math sent me. So you've got a human skull. It has a hole in the top drilled, or like a decent size hole, maybe a quarter size, 50-cent size. What do you think?
Let's say big enough that you can kind of look through and make memeasurements. And
yeah,
stuff
like an
that.
egg will fit in the hole in the top, and all of the other holes have been filled in.
Yeah, and also very important too. If you've ever seen like a sandcastle being filled in, or like poured water on sand, you'll notice that sometimes it'll fill up, and then like there'll be like a little dune that hasn't been filled up, but once the water level reaches it, all the water kind of like runs into it. If we got a bunch of pieces of construction paper and layered them within the human skull, we could make a bunch of we could just put a bunch of stacks of paper where the paper is just one sheet of paper each and fill up the cavity.
Yeah. So a human skull, or rather like an object that looks like a human skull, it could be a human skull actually, or an object that looks like a human skull where the only hole is a hole on the top of it that doesn't ordinarily exist, I guess. Jeez, look at you all should be so thankful for the efforts that we go to make entertaining math problems. Okay, so we're filling up a human skull with a liquid, and there's no holes except the hole in the top because of some wonderful spackle you all got from a hardware store.
No, okay, now that we've established the shape of the human skull and everything like that, the question is, how quickly is the water level rising at what? Let's say that like we're filling up the skull with water from the sink, and the water level will be increasing.
Or water, or do you want some other liquid of your choice?
Yeah, let's say we pour the black goo from the Great Abyss into the skull, and we're pouring it at a constant rate. And let's say we have a little sailboat on top of it. How quickly is a sailboat rising at a given point in time? How do we measure that?
Jesus. Black goo from the Great Abyss. Dude, that stuff sticks to your carpet like none other. This would be a great time for an advertisement on goo be gone, you know what I mean? If you have goo from the Great Abyss that's tracked all over your carpet, it's awful.
No, but we do have advertisers like... Brilliant's mission is to help people achieve their learning goals. So whether you're a student, a professional brushing up on learning cutting-edge topics, or someone who just wants to understand the world better, you should check out Brilliant. They have a new course which goes nicely with this problem episode about calculus, and that's their Calculus in a Nutshell course. They use visual and physical intuition to help guide you through the pillars of calculus. To support your education in math and physics, go to www.brilliant.org/breakingmath and sign up for free. The first 200 Breaking Math listeners can get 20% off the annual subscription, which we've been using. And now, back to the episode. We have a human skull. The skull is being filled up with goo from the black abyss at a constant rate. Let's just say, for the sake of this problem, 100 milliliters per second. Let's say, and let's just choose the halfway point. When the skull is halfway vertically full with this liquid, how quickly is the water level rising?
Okay, now let me ask you real quickly. I'm curious, when you have a very obscure shape, like a human skull or, some obscure vase or any other container, you have some information. We gave you information that you need. How the heck would you find out what the surface area is at the halfway point? How would you know that information?
Well, let's say we had a can. A can is about a circle all the way through. Mm-hmm. So all we have to do is get some calipers and measure the diameter of the can. Mm-hmm. Similarly, with a vase, it is radially symmetric. Mm-hmm. So all we'd have to do is measure the diameter as well, and we'd know the cross-sectional area at every given point. However, for an irregular shape, we would have to be familiar with the entire shape, inside and out.
Yeah, so how the heck would you be familiar? So how would you get that information in this day and age? Would you have to do some sort of Archimedes thing where you take a bath and put the skull underwater and figure out the entire volume, then divide that by half?
It's interesting to actually bring up that area is harder to measure than volume in a 3D world.
Yes.
There's a machine that I've seen that does this, that you push a piece of leather through it, and it has these hooks that are not these hooks, but they're these little gears that go through, but it's still discrete. And there's various ways that you can measure the surface area. For example, you can pour a very, very small amount of a very thin oil on top until it's let's say a micrometer thick, exactly a micrometer thick, and then determine how much oil you needed to fill that up, and then get the area from that.
Okay.
But basically, I think what Gabriel's bringing up specifically too is that we're dealing now with calculus, which means that we're dealing with instantaneous rates of change and things like that, which we're going to talk about in the next section.
Yeah. Now, let's just say, with respects to the skull, just because I'm curious, in order to find out the halfway point, you'd have to be like a dolphin and use echolocation or something like that, right?
Yeah, you're a dolphin. You won the skull in a battle of wits with your fellow dolphins. You're ready to take over the world. You're filling it up with the goo from the black abyss. You're using that in your generator, and you want to know how quickly it's rising because you have reasons.
Yes. So a dolphin would be able to, using echolocation, would be able to figure out the exact halfway point. Is that what
yeah, so we're assuming, basically, the point of all this is that we're assuming perfect knowledge about the skull.
Okay, very good. So we
know the cross-sectional area at every height.
I'm not meaning to be such a pain, but it just makes me curious. How would one figure out this information? But the audience, all you need to know is that you have that information, whether you're a dolphin or whether you're, some sort of interdimensional being, you have that information. So, without further ado, we are
use an MRI machine.
Yes, use an MRI machine. All right. So, this next section of this podcast, we're talking about this problem involving filling a skull with a liquid, which we've already identified. Let's talk about something called instantaneous rates of change. Now, this is an important concept for anybody, even high schoolers who have a basic knowledge of calculus. Now, they do these math problems, and if I may be so bold as to say, are boring as all get out. You study instantaneous rates of change, but how often do you really understand what it is that you're doing? So let's take a moment and talk about instantaneous rates of change.
All right, yeah. So who's a character from Fast and the Furious?
Oh gosh, I've never seen any of those movies.
Let's just say that I've never seen it, but let's say it's called Max Furious.
Max Furious, dude. You all seen Fast? Max Furious.
Yeah, so Max Furious is trying to beat up the drug dealers or whatever he does, and he's in a car and it speeds up from a dead stop.
Are we going to lose listeners because we're making up stuff that's not in Fast and the Furious? This is a math podcast. This is not a Fast and the Furious podcast. And for all of you wonderful fans of that movie, I'm sure it's phenomenal. I'm sure it's beautiful. And I know that we're about to slaughter it. Oh my goodness, we're about to slaughter it. But this is all in the name of explaining a math concept, specifically instantaneous rates of change. So I'm bracing myself for the brunt of hateful emails and hateful reviews that we're about to get.
So anyway, Max Furious starts with 0 velocity, and that increases over time. So you can imagine this car has a speedometer like any other car, and Max Furious, the hero of Fast and the Furious, looks at the speedometer at let's say 3:35 p.m. and let's say it says 40 miles per hour. That is his instantaneous rate of change.
And this is crazy. Instantaneous rate of change. So one of the things that is really mind-blowing about this is we've spoken before about calculus, and you have your position, which is how do we explain position? It's like where we start with, right?
Yeah, position is like how much distance there is between you and your starting position.
Yeah. So in calculus, there's a lot of concepts here, including position. The derivative of position. You got to use calculus for this. The derivative of position over time is velocity, or your speed.
And if you notice the units, position is meters or like feet or whatever.
Yes.
And time is like hours or seconds or whatever.
Yeah, so like 3 feet.
Yes.
Per second.
Yeah, so the derivative of something over something will have units of that first thing over the second thing.
Yes.
So the derivative of position over time will be in meters per second.
Yeah.
Now, let's say you're doing the derivative of position over color. Like you want to see how much the position changes of stuff based on the color of the environment or something like that. Then it will be in the bizarre units of position per color.
Yeah, exactly. So basically,
I don't know how to interpret that.
We're just talking about keeping our units straight, because everything we're talking about here, everything, the consistent idea of anything meaningful at all is one thing in relation to another thing. And in this case, it is your speed in relation. So with position in relation. So
you're saying, that the derivative of position with respect to time is equal in units of position over the units of time, which is in meters per second or miles per hour.
Yeah.
And if you notice, what's up?
Oh yeah. Well, I was just going to say that what the thing that really got me thinking was you have position. The derivative of position is velocity. The derivative of velocity is your change in velocity over time is acceleration. The derivative of acceleration is jerk.
Oh, right before we go into that, the reason why derivative of velocity is acceleration is because you can imagine let's say right now you're going 40 miles per hour, and in 1 second you're going 50 miles per hour. That means in 1 second you increased 10 miles per hour.
Yes.
So your acceleration was 10 miles per hour per second.
Yes.
Which works out to something better. You can multiply hours and seconds, but I don't feel like it.
Yeah. No. I understand. My issue is that you don't necessarily always have the same acceleration. You can have a variable acceleration.
If let's say someone has a very unsure foot on the acceleration, and the car lurches backward and forward, like on the interstate, that means that the acceleration is constantly varying. And actually, it's interesting is that the amount of lurch that you feel is exactly proportional to acceleration, which is actually something that Einstein used in his second theory of relativity.
I didn't know that Einstein had a sequel.
Oh yeah, the general theory.
Well, I knew that. Oh, second theory of relativity is the general theory. I knew that. I knew he had two theories, but I've never heard it in terms of like the sequel.
Yeah, I've never heard it either. I just do things sometimes. I just say things.
Okay, this is funny. Yeah, so anyways, the reason why I brought all that up is because there's this concept a thought experiment that I think that we talked about this in a previous episode called Zeno's paradox, where you talk about the difference between something at rest and something movement or in movement. What is the exact moment that you begin to be in movement? And that's a very hard question to ask because it's a continuous thing, and continuous things are infinite. You know what I mean?
Oh yeah. You're dividing infinitesimals by infinitesimals to get like 2 miles per hour like type numbers.
So,
it's kind of it's fun, and the foundational aspects of derivatives is you take a thing called a limit, which is like let's say that at 305 you're somewhere, and at 310 you're somewhere else, and you calculate the average velocity. Well, if you did it at like 305 and then 306, you get something much closer to what the instantaneous rate at what 305 would be. And then at 305 and 305 in 1 second, you get even closer. And the derivative is like, if you kept going forever, what would you get?
Correct. Yeah. Now, obviously, all of this relates to filling up an obscure shape, and for the purpose of this episode, a skull with a liquid and the rate of change of that. But still, calculus. No matter how many times I am now 35 years old. In my 35 years, I never ever cease to be amazed at calculus as I'm trying to explain it to somebody. It always blows my mind.
I also have to point out that Gabriel looked at his watch when he was thinking about what age he was.
Yeah. Oh, why did I do that? I don't know why I did. I don't exactly know why I did that. Before we talk about the rate of change of a liquid that is filling up an obscure shape, such as a skull, let's talk about a much, much, much simpler problem. Sophia, do you want to introduce a simpler problem?
Sure. Let's say you have literally a box that you're filling with water from a tap. The tap is dispensing 100 milliliters of water per second. And remember, 100 milliliters is 100 cubic centimeters. And let's say that the box, let's say it's pretty tall, whatever height, it doesn't matter what height it is, but let's say it's 10 centimeters wide and 10 centimeters deep. So it has a cross-sectional area of 100 centimeters squared. That means that, so let's say we're pouring in water, right, at a constant speed. After 1 second, how much water has been dispensed?
Well, that's a pretty easy problem then, and it's easy because we've got a consistent shape. It's the same shape all throughout.
Oh yeah, but I'm saying if the tap dispenses 100 milliliters of water per second, after 1 second we have how many milliliters of water?
100 milliliters.
Yeah, which is 100 centimeters cubed. And remember that the definition for for the volume of something is how high it is times the cross-sectional area it is, if it's like a perfect extrusion. And by extrusion, I just mean imagine making something out of Play-Doh and pressing it through something. So 100 centimeters cubed divided by 100 centimeters squared, which again is the rate of flow, divided by the cross-sectional area, is 1 centimeter. So basically, and since it happened over 1 second, the water is rising 1 centimeter per second.
Yeah, with this particular problem, you don't even need any calculus whatsoever.
And if you think about it, like let's say this was like a tiny, like a really skinny, like square, like tube thing, and it's 1 centimeter by 1 centimeter, it would rise 100 centimeters in 1 second, right?
Yep.
And that makes sense. It could be like whoop versus like whoop.
Exactly.
But yeah, so all we have to do if we know that we're filling up a box from a tap is take the cross-sectional area of the box and take that and have it divided by the rate of flow.
Mm-hmm. Yeah, exactly. Now, there's going to be a difference between the very simple shape like this shape, a cylinder or even a cube, and the skull. So let's briefly talk about how we would do the same problem with a slightly more complex problem where you've got something that's not so simple as a cube.
Yeah. Oh, yeah. And before we do that, I want to make a note that the box doesn't have to be, it doesn't have to be a box. If that had been a cylinder, all we have to know is that we know the cross-sectional area to fill up the cylindrical tube. You could also imagine it like, imagine we had a bunch of pancakes with, I don't know, Totoro on them, and you have a stack of Totoro pancakes, and you make a tube that is Totoro shaped. All you have to know is the area of Totoro to know how quickly the water level is increasing in this Totoro tube.
I've never heard Totoro until you mentioned it just now. Is that
he's like this, I just got into Hayao Miyazaki. He's this, he's this, family film director from Japan who designs these visually incredible films. Like, I know I'm very late to the bandwagon, but...
Oh, wow. Okay. Very good. Very good. So, talking about a slightly more complex problem, I'll go and read this one here. Suppose you have a cone that is 100 centimeters squared at the top and is 1 meter tall. When it is at the vertical halfway point, how fast is the water level rising? We can conceptualize this cone as a bunch of cylinders of increasing size.
Yeah, I was like kind of like one of those things that scoops honey out. I was thinking,
it's
or like Devo.
I don't know what either. What's Devo?
Devo, the band from the 80s.
Okay.
They had these hats that were basically like a bunch of like smaller cylinders on top of each other.
I was not aware of that. I'm gonna have to Google search Devo hats.
I'll do it right now.
Okay, hang on. I'm gonna Google search Devo hats real quick. Oh my goodness, Devo hats! They're the red things they're ridiculous. I'm sorry. We should edit that part out. Whatever. I don't care. I call them.
No, Devo would like you calling them ridiculous.
Okay, interesting. Yeah, it looks like a Lego thing. But there needs to be a Lego version of Lego Devo. I think it's like Russian dolls almost. Dude, all listeners, do yourself a favor. Google search Devo hats. Let's try to make that go viral. Let's bring those back.
So yeah, you can imagine like you have this cone, right? And you can approximate it as like at the very, very bottom of the cone, you have this tiny little cylinder, maybe the size of a pencil eraser. And then right above that, you have like a disc the size of like a few stacked coins. And then the size of a few more stacked larger coins. And you
Larger
have
coins.
yeah, and you have this bigger and bigger thing until you have this.
Ooh, CDs. How about? Can we do CDs?
Yeah, it goes to CDs, then it goes to laser discs, and to the whole bigger,
like car tires, maybe a flatter car, like pizzas. Maybe.
Although then we're getting way above 100 centimeters squared.
Oh,
but yeah, exactly. It's the same vein. You have bigger and bigger cylinders, and together they look like a cone.
yes.
So when the water is at the halfway point, remember it is filling up the cylinder that is at the halfway point, and it is doing that. And remember a cone. The width at the halfway point is going to be half the width at the point where it's the widest.
Yes.
So and since we're doing area, we have to square it because you go back to episode 1 and listen to Mino's slave. Talk about how you have to take a half, like taking a quarter of something kind of feels like taking a half sometimes. But it's basically 25 centimeters squared. So if we know that we're putting in water at a rate of 100 centimeters cubed per second, and this has a cross-sectional area of 25 centimeters squared, how quickly is the water level rising? Okay,
so from that information, we know that the water is rising at an instant rate of 4 centimeters per second.
Yeah, and if you think about it, it's a lot faster than it was at 100 centimeters squared. And that makes sense, right? Because when you fill up a cone, it would go really quickly at the beginning and then get slower and slower and slower and slower.
So it would be, so the rate of change, so the derivative here, the acceleration would be a constant slowing down.
Yeah, and what's interesting too is that the bottom half of the cone would take something like 1/8 of the time to fill up. The bottom half of the cone, because we would have to cube the 1/2. So we're dealing with different dimensional stuff here. Just wanted to point that out.
Thank you. I'm glad you pointed that out. So we're about to get weird here. We're about to get a little weird. We're going to go from a cone to the strange shape of a human skull. Now, a human skull is a varying shape. You have areas of probably, as you go from the bottom up, generally it gets bigger, but not necessarily always.
Yeah, especially with the human skull, there's a lot of weird cavities within the skull. Like a lot of sinuses and stuff like that. Yeah. And we're assuming right now that we're only carrying out the part of the skull that like let's say we had a bunch of like we said earlier, a bunch of pieces of cardboard or something like that. We stacked them up on top of each other to fill up the cavity we're talking about. Now, let's say that we wanted to know how quickly the black goo from the Great Abyss is filling up the skull vertically when it's at a certain point.
What's our goal? Like, let's just say we filled up a skull with the black goo from the abyss. What are we going to do with it then?
Things. Gabriel, we have no need for money from the human realm.
Okay.
We just need the skull with the black goo.
From the abyss. Okay, I've got a friend who sells artistic skulls. Her name is Liana, actually, on Facebook. She has an artistic channel called Something In Between. And you guys should check out Something In Between and see all of her skull art and all the black goo. Her and her husband, Matt Stolfitz. Pretty cool stuff.
Yeah, but let's say but so we looked at the Visible Human Project. We found a video on YouTube. It's this thing where they sliced a frozen human cadaver at like I think 1.3 millimeter intervals, and we found out that the cross sectional area of the human skull at about the point where the nose is about 300 centimeters squared. So we're filling it up with black goo from the abyss, from some kind of abyss tap, and is flowing at 100 centimeters cubed per second. It is 100 centimeters cubed per second divided by 300 centimeters squared, which means that the water level would be rising at about 3.3 millimeters per second.
Correct. So in order to solve for an obscure shape, you just have to have when you look for an instantaneous rate of change at that instant. What's the rate of change?
Yeah. And if you imagine that we had like some kind of like tap that was delivering a whole liter per second,
Mm-hmm.
then at the halfway at the nose point where it's 300 centimeters in cross section, it'd be filling up at about 3.3 centimeters per second.
It's not possible to solve this problem unless you do have the fact that you're at the halfway point.
Yeah, but we have the advantage of being mathematicians where we know everything within our world.
Correct. Yes, exactly. So assuming it is in fact the halfway point, that's the information that you need to solve.
Or whatever point you care about. It doesn't have to be halfway point.
Or third point.
If you wanted to see like if it was like when it reaches the eyeballs, how quickly it'd be increasing. I don't know. That's one thing about this problem that I never understood from calculus is why anybody would care about how quickly the water level is rising.
Yes.
I can't think of a reason why that would matter in engineering.
If you're about to die and you're calculating how much oxygen you have left versus how much time.
But even that would be volume.
Okay.
The water level rising would be like if you had like a boat.
Will somebody please email us and tell us why the heck would you care how fast the water level is rising? We're not talking about volume here.
And we're actually interested. If you are an engineer and you do need to know how quickly the water level is rising within a tank for some reason, please let us know. We'd be very interested in hearing.
Yeah, and we're not just talking about when it fills up, because again, that's a volume problem. We're specifically talking about the rate of water level rising. I don't know. I can't think of a reason.
For more information on what we're talking about, listen to the rest of the episode, the previous bunch of the episode.
Some further problems. Now, here is an interesting spin on the above problem. What if the black goo from the abyss, what if it is changing the flow rate over time in a predictable way?
Or some way that we at least know.
Hence predictable way.
Oh yeah, but I mean like in the mathematical sense where it's not actually predictable, we just happen to know what it'll do. Like, I guess it's predictable.
Okay, and we want to know how quickly the water is rising at a certain level. We need to know the volume of the skull below that point, that like the eyeballs or the nose or whatever. We need to know the volume of the skull below that point, the point at which that much black goo was delivered by the black goo delivery system. I mean, how does that work? I don't know about the plumbing with the abyss, but whatever. That's not my...
Well, this would be the integral of the black goo rate function over time.
Okay, exactly.
An integral is like adding up like little slices.
Exactly. Okay, good. So to get the rate of the goo addition at that point in time, and we need to know the cross-section area at the level that we're concerned with.
Yeah, so basically what we've shown here is that we get one rate of change from another rate of change, and we've done it with a simple word problem.
Yes. So all of you who are wondering, what do you need math for? Well, your answer can be you now know how to find the instantaneous rate of change of black goo when you're filling up a skull.
And if everything goes to plan, that'll matter quite a bit.
Yes. It will. I'm Gabriel.
And I am Sofía.
Who usually goes first, but I stole the first spot there.
No!
Is it? So are we done? Like, should we add some evil laughter or something?
Like, wait, where's that evil laughter?